In the last video, when solving a system of differential equations, at one point we had to solve the characteristic polynomial, and that was a quadratic equation. Well, when dealing with quadratic equations, there's three options. We could have two solutions, which is what we did previously. We could have one repeated solution, which is what I'll look at now, and we could have complex solutions, which we'll deal with in the next video. But for now, let's look at what happens when we have a single repeated eigenvalue. I'm going to look at this system here, x prime equal to 7x plus y and y prime equal to negative 4x plus 3y. To write this in normal form, we have x prime equal to our matrix. The first row will be 7, 1. The second row, negative 4, 3 times x. We need to start by actually finding our eigenvalues. So this looked at the determinant of a minus ri. So we subtract r from the diagonal. 7 minus r, 1, negative 4, and 3 minus r. When we do this, I multiply diagonally, so I have 7 minus r times 3 minus r, minus the other diagonal, which is negative 4. Multiplying this out gives me 21 minus 10r plus r squared plus 4. Rewriting, I get r squared minus 10r plus 25, which is r minus 5 squared. And I really want to know, when is this determinant equal to 0? Well, we can see that happens at 5, and this time there's only one repeated root. After this, our next step was to find the eigenvector. In order to do that, we actually plugged in 5 to this matrix here. 7 minus 5 is 2, 1, negative 4, and 3 minus 5 is negative 2. I multiply that by a generic u1, u2 vector, and I should get the 0 vector. If we scroll down a little bit, the first row gives me 2 times u1 plus 1 times u2 equal to 0. The second row, negative 4u1 minus 2 times u2 equal to 0. And we can see that these equations are essentially the same. If I multiply the first one by negative 2, I get the second one. So I only have to consider one of them. We have 2u1 equal to plus u2 equal to 0. I'm going to solve this for u1 to get that u1 is minus 1/2 u2. So to get my actual first eigenvector, I'm going to pick a number for u2. I'm going to pick 2 and solve for u1. I would get negative 1. Since 2 times negative 1/2 is negative 1. And we could have let u2 be equal to 1 and had negative 1/2 1, but we picked 2 to eliminate the use of fractions. In the past, when I wrote my solution at this point, I would have c1 e to the eigenvalue t, so e to the 5t, times this vector, plus c2 e to the other eigenvalue times t times the other eigenvector. However, I don't have this. This part is missing right here. So instead, we need to try to figure out something to replace it. So we'll erase this for now and see if we can figure out something to replace it. Let's start by just seeing if I can do something like t e to the 5t times this eigenvector. So I'm not quite saying this works yet, but I want to know, what about this? Will this work? Or do we run into a problem? Well, our differential equation says x prime. So I'm only going to be considering this vector right now. The derivative of this, using the product rule, would be C2 e to the 5t times u1, where u1 is this vector, negative 1, 2, plus 5 C2t e to the 5t times u1. And according to my differential equation, this should be equal to a times x. So a times C2 t e to the 5t times u1. Well, I'm going to go ahead and equate things. You'll notice that both this term here and this one over here have a t in them, so they should be equal to each other. I have 5c2t e to the 5t u1 is equal to c2t e to the 5t a u1. I can go ahead and divide through by c2 and t and e to the 5t. When I do, this side becomes 5u1 equal to au1. That's 0 equal to au1 minus 5u1. And factoring out the u1 gives me a minus 5i times u1. Well, this is exactly what I solved in the first place to get u1. So this does not give me any new information here. However, if I come back up here, this term right here has, or does not have a t in it. It's just c2 e to the 5t u1. And it should be equal to the thing on the right-hand side without a t, which is just 0. So this only works if u1 is equal to 0. That's the only way to make this 0. And that is not helpful for us. So this actually will not work. Instead, we're going to have to adapt it a little bit. So I will erase all of this. And we're actually going to add something on top of it. We're not going to completely get rid of this. We're just going to include something else as well. So this time I'm going to add c2 e to the 5t times a u2, a different vector. And let's see if we can figure this out. So since this didn't work, I'm going to go ahead and erase it. So we can try to see if this new thing will work and how we might go about finding it. For simplicity's sake, this should work no matter what C1 and C2 are, so I'm just going to go ahead and let C2 be equal to 1 to make this work slightly easier. So now I'm considering this huge big vector here. Taking the derivative, assuming C2 is equal to 1, I have e to the 5t times u1, which is my vector negative 1, 2, plus 5t e to the 5t u1, plus my next piece here would be 5 e to the 5t u2. And once again, our differential equation says this should be equal to a times this thing, t e to the 5t u1 plus e to the 5t u2. And once again, I'm going to equate pieces that have a t and pieces that don't. So if I look at the pieces that have a t, I have 5t e to the 5t u1. The right-hand side is t e to the 5t a u1. Once again, I can cancel my t and e to the 5t from both sides. I get 5u1 equal to au1. Getting everything to one side, I have au1 minus 5u1. And then factoring out, I have a minus 5I times u1, which is exactly what I had before. Exactly how I found u1. So just like before, this is not new helpful information. However, this time when I look at these terms that do not involve a t, I have e to the 5t u1 plus 5e to the 5t u2 equal to e to the 5t a u2. I get u1 plus 5u2 is equal to au2. I'm going to get my u2's together. I have u1 equal to au2 minus 5u2. Factoring gives me u1 is equal to a minus 5 u2. And this is what I need. I need to be able to solve this for u2 to end up getting my solution vector appropriately. So let's try to do that. I forgot an I in here. A minus 5I. We already know what A minus 5I is. That's the matrix we dealt with previously. 2, 1, negative 4, and negative 2. We've already dealt with that one. It's the exact same one that we have over here whenever we found the original U1. I'm going to multiply it by some vector. I'm going to use the letters V1 and V2. And that should be equal to my vector U1, which was the negative 1, 2, the one I found originally. When I multiply out, this becomes 2V1 plus V2 is equal to negative 1 is my first row. My second row, negative 4V1 minus 2V2 equal to 2. And once again, these should always have infinite solutions, so I'm only going to deal with this first equation. 2V1 plus V2 equal to minus 1. I'm going to solve for V1. I get negative 1/2 minus 1/2 V2. I then need to pick a number for V2. I'm going to pick 1 and figure out what V1 needs to be. If V2 is 1, I have negative 1/2 minus 1/2, which is negative 1. So there's my new vector U2. So I can now finally write my answer. C1 e to the 5t times U1, which we had found originally, to be negative 1, 2, plus C2 times t e to the 5t times the vector I had originally, negative 1, 2, plus C2 e to the 5t times U2, negative 1, 1. So I have my solution. And let's suppose we want to take it a little bit further. Let's suppose we know that if t is equal to 0, then x is equal to 1 and y is equal to 1. Scroll up just a little bit here. The top row on each of these, the top one gives me x equal to negative c1 e to the 5t from the first vector. The second vector gives me negative c2 t e to the 5t. The third vector minus c2 e to the 5t. The second row, this first vector here, gives me 2c1 e to the 5t. The second vector, second row, gives me plus 2c2 t e to the 5t. And the third one would give me plus c2 e to the 5t. Now, I know that x is equal to 1 if t is equal to 0. So I have negative c1 times 1, negative c2 times 0, so I'm going to skip this term, minus C2 times 1. My second equation, I know y is equal to 1. I have 2C1 times 1. Once again, this middle term, if I let t be equal to 0, will become 0, and then plus C2. We can just add these two equations up. That gives me 2 is equal to C1. I then have 1 minus C1, or 1 equal to minus C1 minus C2. So 1 equal to negative 2C1 minus C2. So that means 1 is equal to negative 2 minus C2. 3 is equal to minus C2, or C2 is equal to minus 3. So now if I scroll up, I can change my C1 and C2 appropriately. I said that C2, let's go ahead and erase these plus signs as well. I said that C1 was 2, so I'm going to write a 2 here. And I said C2 was negative 3. So with that, I finally have my solution.